Hey, everybody. Okay. So today I want to continue with our discussion on climate change that we started last class period. And let me get this working here. There we go. Okay. So we're still in the same place in the course syllabus and that course outline. And the goals remain the same here. Today, I really want to focus on the last of these bullet points here. So, want to really talk about the effects of climate change on coastal ecosystems. So, you remember that last class period we were talking about the relationship between temperature and greenhouse gases, and most of our focus has been on carbon dioxide because that's where most of our anthropogenic impacts are, more than 75%. In fact, the gases that we're putting into the atmosphere are specifically carbon dioxide. And so I focused a little bit on this little trend we've got right here, right? So this is about a 10,000 year period where we've had relative stability in the climate. So when we came out of the last ice age, and that really started or kickstarted a real significant change in humanity's development. We were able to establish agriculture. We went into our industrial age and then have now entered our information age on top of that. Part of that progression has been utilizing fossil fuels as a source of energy to drive that change. And so the consequence of that is you can see that the carbon dioxide level has risen beyond what we have seen for more than 800,000 years, and it's projected to continue to increase by another 50% just by the end of this century, right? So over the next 75 years. And that could then cause a subsequent increase of 3.5 to 4 degrees Celsius just because of that greenhouse effect caused by those greenhouse gases. Now, remember the difference between our current climate average and the depths of the last ice age were only about 5 degrees Celsius, right? So degrees Celsius and degrees Fahrenheit are not the same thing. And degrees Celsius, because of the magnitude there, really that's a significant change in global averages and has significant impacts on the biogeochemical cycles on the surface of the Earth. Okay, so we also talked a little bit about lag time, right? So I won't rehash all of this, but we know that there is a lag between when we see changes in these greenhouse gases versus when we see change in temperature. The earliest of those really tend to show up about 40 years, and that is based in the oceans. And then some of the lag in some ways as the oceans then affect other elements of the earth can continue to increase for some time after that. And again, what we see with carbon dioxide, those lags are true for all of the greenhouse gases, right? It's not unique to carbon dioxide. It's actually all of those greenhouse gases where you have that lag effect. And again, the oceans are kind of central to this because oceans act as a heat sink, right? And so you've probably studied ocean currents, right? And we'll look at that a little bit more in upwelling and that sort of thing. But there's a lot of there's time that's involved, and that's part of what that lag is about. Is it takes time for the oceans to heat up. They don't heat up uniformly, as we're going to see, and so it takes some period of time before then you see the effect of the oceans on the rest of the Earth. Okay, so the change over time, even just over 50 years, which again is like, when we're talking about geologic time frames, very different than human time frames. So 50 years seems like a long time. I know in the infrastructure work that I've done over the course of my career, we're often looking at 75-year project lifetimes, for things like dams and levees and other major infrastructure projects. Um, I don't know about you, but I'm not planning on working 75 years. 75 years is an entire human lifespan, on average, here in the United States at least. And so, 50 years is a long time. So when you look at warming over the last 50 years, what you see here is changes that clearly have an increasing trend at the surface, at the mid-level, and even in the deepest parts of the ocean. And so the upper, as you might expect, warming in the upper ocean is actually the highest, and it accounts for about 63% of the total increase in the amount of stored heat in the climate system in the time frame that they studied from 1971 out to 2010. Um, so the other thing to consider here is that that warming is not homogeneous across the surface of the Earth. In fact, if you look at the second graphic, what you'll see is that there are hot spots and there are cool spots, and that distribution is not equal. And part of that has to do with the upwellings and circulation currents that I mentioned previously. And again, you probably studied those in some of your other coursework associated with your degree. So, this warming contributes to a whole variety of issues um, related to coastal communities, including our plant communities that we're studying. And that, means contributions to sea level rise, ocean heat waves, coral bleaching, melting of ocean terminating glaciers and ice sheets around Greenland and Antarctica and throughout actually the Arctic Circle. Um, and the heat that's already stored in the deep layers of the ocean. So we talked about the surfaces where you see most of that heat accumulation, but what's happening down in the deep ocean is equally problematic because that's heat that is eventually going to be released, which commits the Earth to at least some additional surface warming in the future, right? So just because you may not see, if for some reason we didn't see a continued increase at the surface, that doesn't mean we're not going to continue to see heating because we've got heat building up in the lower parts of the ocean as well. And this has changed. So if you look at this graphic, you can see how this has continued to change from the 1950s through this 2006 is what they looked at here. Um, and that the heat content of the global oceans, so that the entirety, has consistently been above average since about the time I graduated from high school, right? So late 1980s, early 1990s, when I was starting college, climate change was really starting to come into focus because we were starting to sort of see some of these trends. Scientists have been measuring these things for a long time. We talked about that already, but we really were starting to see some significant changes at that point. So this has in some ways been the environmental story of my career, is watching these kind of changes unfold and trying to figure out how do we mitigate against these. So what are the known impacts of climate change on coastal communities, and what are we still figuring out? So we're looking at things like sea level rise, temperature, precipitation. Hurricanes are certainly garnering a lot of attention. Certainly had some activity, to say the least, this year, but extending back over many years, there's been some trends. And then also ocean acidification. So let's unpack some of these a little bit. Sea level rise. So eustatic or global changes, there's some that are natural and there are some that are anthropogenic here. But all of these are related to changing climate. So there's thermal expansion. So the water getting, again, as substances warm, right? There's more vibration that's occurring in the atoms, in the molecules that make up that substance, whatever it is. And when things start to vibrate more, then you get expansion occurring between those atoms and molecules. So that's part of it. So the oceans are actually they're becoming less dense for any given volume, right? And then we also have glacial melting, which is contributing new water to the oceans. Now, if you would like, I've contributed a number of resources that you can go and visit here. So I would encourage you to look at these. These are interactive tools that you can use. I use some of these in my environmental science classes as well, that look at sea level rise, so you can look and see what's happening right here in Galveston if you choose to do that. So there's some pretty interesting things there, and I encourage you to spend some time on them. When we look at predictions in global sea level rise, essentially we're utilizing models that you would probably be somewhat familiar with, trying to determine what's going to happen. And so those models are using data that we've already collected in the past to tune the model so that it can predict what happened in the past accurately so that it can make projections forward. And then from that, we want to try and determine, okay, is how does the how does what is happening actually in terms of our measurements moving forward, how does that compare to the model so we can continue to develop that model and make better projections as we move forward. So, what you're seeing here in this data here are trends based on actual instrumentation values. So these are actual measures, right? And so those orange and red lines are tide gauge and satellite data, respectively. Okay, and we have tide gauges data that goes back much further than we have reliable satellite data. The blue and green areas here are what the model projections are. Now, the question I'd ask you as you look at this is, does this provide evidence of increasing sea level? And I would argue that yes, it does, right? You can see that the trend here over this period. So remember last class period, we talked about 30 years when we're talking about climate being a kind of a minimum time frame. And we're in that zone here, and over this 30 years, the trend from the data that we have has been pretty consistently climbing. So that definitely suggests increasing sea level, and potentially this would be evidence towards an increasing or increasingly warm climate, right? Okay. So, but if we go back further, right, we have tide gauge data that goes back to the 1850s. Now, some in that gets increasingly sparse the further you go back, right? So there's fewer tide gauges. They're not necessarily equally distributed around the globe, so the data gets a little patchy. Um, Actually, we have tide gauge data along the Texas coast that goes back to the 1800s. So prior to 1950, it's the reliability of the data, our confidence in the data is less, and that is so you can see that described here in this kind of gray shaded area around the actual data set in the black line. So you can see that gets wider as we go back, and there is quite a bit of variability there too. Um, but clearly there's a trend here, right? So if I wanted to strike a line through here, that line is going to be relatively straight. Okay. So adding more data to our data set that we saw in the previous slide. Okay. And if we go back further still, we can do modeling based on past air temperature and sea level reconstructions from tree ring data and other proxies. So we talked about proxy data in terms of ice cores, for instance. So we can go back quite a long ways, and we see fluctuations in climate. Even within this 10,000 year period that we've had of relative stability in our climate since that allowed us, the advent of agriculture. Even there, remember, it kind of fluctuated around that average line. And so you can see that reflected in the data here. So if we then take this and we use that model to start to do projections out, um, look at that line, right? Look at this projection, right? So the, in my field, so in aquatic toxicology, a lot of times, a lot of the work that I've done, for instance, is what we refer to as multiple lines of evidence, or MLE type of data composition. So we might be looking at 3 or 4 different lines of data to see how those things line up and if they point to the same source, right? If I'm looking for a toxicant in the environment, this is similar. These models utilize a lot of different data sets in order to try and determine, okay, what's the likely outcome here, and do these data sets agree? And what we're finding is that, in fact, they do agree. And that gives us more confidence in these projections, right? So that's concerning. um, But how realistic are these predictions in terms of, how good are these models, and is there bias potentially built into these? Because, depending on who you're talking to and what you're reading, there's like, climate change is this made up thing, this made up hoax that, people are just trying to get people, excited about new business ventures, right? We're going to make everybody buy electric cars or whatever it is. You might hear all kinds of things, but um, I want to tell you, in my experience, in my entire professional career, dating back 35 some odd years, and having an interest in this since I was in high school, because this is when we really started to see a lot of these changes. I followed this science relatively closely, and actually, some of my own work along the coast, especially that work that deals with coastal ecology, kind of an extension of the toxicology that I've done. Sea level rise is an issue that we're dealing with. And so, and that has impacts on some of these coastal communities, and in fact has impacts on the toxicology of the sediments and those things as well. So, looking at the data around climate change, there is a lot of really good research that has been done supporting the development of these models. And the predictions are synthesized by the Intergovernmental Panel on Climate Change, the IPC for short. And what they've done, working with all of these scientists around the globe, working on gathering all of these different data sets, proxy data, direct measures, right, across a variety of different parameters, is they've tried to develop scenarios that will help us in terms of adaptive management, right? Looking at, okay, this is what we're seeing happening. This is a problem. How are we going to manage this problem, right? So again, going back to the purpose of science, which is to inform decision making, right? So they've developed a handful of different scenarios, and the middle of the road scenario, this is the one that I want to show you here in a second, but the middle of the road scenario is this. We're continuing to work on CO2 emissions. So through things like you've probably heard of the Paris Accords, the Paris Agreement, whereby all these different governments, as part of the United Nations, are coming together to make commitments to reduce carbon emissions to the atmosphere within a set period of time. Now, as international treaties go, even the Montreal Protocol, as amazing as it was, 185 different countries coming together to reduce ozone, actually to reduce chlorofluorocarbon emissions in order to help protect the ozone layer. The model of this approach is similar to that, and getting all these different countries to come together. But as you probably have seen, it's a little more fraught. We don't have quite the uniform approach that we had with the Montreal Protocol. So here, in this model, they're saying, okay, well, under these agreements, carbon dioxide emissions are falling by the middle of the century, so 2050, but we don't reach net zero even by the end of the century. And so all the socioeconomic drivers, that are producing these CO2 emissions kind of follow their historic trend, which is this kind of upward increase with no real notable shifts. And the consequence of that is temperatures rise by another almost 3 degrees Celsius by the end of the century. You're going to you're tired of me saying this, I'm sure you're tired of hearing this, but remember the difference between a normal, nice climate and the end of the last ice age. A few degrees Celsius yields really large changes in terms of what's happening in the environment. By the way, the IPCC reports are available freely to you. You can Google IPCC climate report, and it'll bring up the latest one and all the ones prior to it. So if you want to spend some time with that, it's interesting reading, and there's a lot of good information in there generated from really good data. So, okay, so how closely are real-time conditions following the IPCC predictions? And while this only covers, about 25 years going back since their first models, right? So the models are relatively young. Um, what we are seeing so far is the models are also relatively conservative and aren't actually, while they're accurately describing the trend, the overall trend, they are not describing the magnitude of that trend accurately, right? So what we're actually measuring versus what the model predicted are not the same. And in fact, what we're measuring is higher than what the model was predicting. Now, they are continuing to work on the model, and just like hurricane models, I remember when Hurricane Alicia hit Galveston Island in the early 1980s, 1983. I remember seeing on the news as a child the cone of uncertainty, right, when they were making those predictions. And 3 days out before Hurricane Alicia hit Galveston, the cone of uncertainty was essentially the entire Gulf of Mexico. Now, the hurricane predictions 3 days out, they can almost pinpoint where that storm is going to go, right? So models continue to develop as that we get more data, right, to feed into those models. All right, so if these estimates are conservative, what does this mean for future sea level rise? So, for instance, where is Galveston, where we are, where is that likely to fall? Is it going to be higher, lower, spot on with the predictions? Well, if you look at what's actually happening on the Texas coast, right? So you look at these measures. So this is data. I know I've referred to this in the past, but so this is NOAA data from Galveston, the Galveston Pier 21. And, we're seeing a rate of about 25 inches every century in terms of the rate of rise. So, that's kind of a foot a century is what we've seen so far. Um, and part of the issue with the Texas coast, and we're going to talk a little bit about relative sea level rise, which is tradition, or actually uh, true sea level rise, which is that expansion of the water along with new water being fed in from melting glaciers, combined with ground subsidence, right? So one of the issues we have in the Gulf Coast and in many coasts globally, but certainly in the Gulf Coast, we have high levels of ground subsidence. Here in the Galveston, Houston area, a lot of that subsidence dates back to high withdrawals of groundwater from our aquifers in our sedimentary soils, which reduced hydraulic pressure, holding those soils up, and consequently the soil sank. In some areas, those rates have really slowed as we got a hold of that, and the groundwater withdrawals were reduced. But in some areas, we have other problems like in the Mississippi basin, where there are so many dams within the Mississippi River, sediment that historically had been feeding out along the coastline is not feeding out at the rates it had 100 years ago. And so the coastlines continue to subside. There's erosion, but there's not new sediment coming in to balance that out. So we've seen sea level rise around 8 inches during the last century, inundating much of the coastline. And again, this is kind of that relative sea level rise. You'll see this referred to as RSLR, okay? RSLR. So the current rate of erosion now is also 5 times faster than it has been in the last 400 years. And our sea level rise rates are not only one of the highest in the country, but actually one of the highest in the world, right here in Galveston. Lucky you, getting to go to college right here where it's happening, the epicenter. Uh, so, um, in any event, this has a lot of effects. It submerges wetlands and dry land, erodes beaches, and exacerbates coastal flooding, as we've seen over the last several decades. So let's unpack that a little further. There is going to be some variation in sea level rise that will be impacted by these very same factors. So vertical land movements, again, subsidence is a really big issue. Accretion, so how much accretion there is, Accretion essentially is coming from our rivers largely. Some offshore flow. There's going to be some accretion from within the Gulf of Mexico. We looked previously at circulation patterns and sediment budgets in along the coast in the Gulf of Mexico, but subsidence is, I would suggest, probably the biggest player, especially in the western half of the Gulf of Mexico. Um, so you have this regional plus eustatic increases, global increases in sea level, and then that's again, you get this relative sea level rise. Um, so RSLR is recorded typically by local tide gauges. And again, I showed you data on what that's going to look like as we move forward, combined with what we've seen already, which is again really remarkable. Actually, having been a resident of Galveston since the 1970s, I've seen quite a lot of change just in that time frame. So again, another URL you can follow. This is a pretty neat tool that you can look at sea level rise in Galveston. I use this tool with my students quite a bit. It's a really easy one to use and a kind of a well, depending on your nature of fun, but it is kind of a fun one to play with because it can give you kind of a sense of what those different scenarios might look like in different parts of the coast. Okay. So with all of that in mind, what are we talking about when we talk about ecosystems, right? So salt marshes, mangroves, freshwater wetlands, and so on. Think these things that we've talked about. So one of the problems we have along the coast, and this is not unique to the Texas coast. In fact, this is something that you would see along shorelines globally. If you think, well, I don't know if you know this, but about 20% of the Earth's population of humans lives within just a few miles of a shoreline, right? We are a species that likes to look at water. And so we tend to set up along shorelines. Now, there's other reasons behind that. I'm joking somewhat, but in terms of those trends. But or the drivers behind those trends rather. But in any event, we do tend to live closer to shoreline. So a large proportion of our population lives near coastal shorelines. And that is true here along the Texas coast as well. Um, the consequence of that is there's a lot of hardened land surface that comes along with development, right? So when we build a neighborhood, we're not only putting in houses, we're putting in roads, we're putting in supporting areas. So think light commercial, light industrial. That creates areas that really aren't habitable for these coastal marshes. And so when you have something like sea level rise, right? Um, the the reaction of the plants is that those plants are going to try and migrate upwards. They're going to try and Spartina alterniflora, which is able to rapidly colonize using those rhizomes that you've seen in the lab and we've talked about in class. What happens there is they're going to try and move uphill because remember those plants, they need to live, they're evolved to live in that intertidal zone. So it can't be too deep, they can't be too shallow. So they're going to move uphill. And really all of the plants that are adapted to these shorelines are going to be doing that same thing. So they stay in their zone of tolerance, right? So if you put something there that's going to prevent them from moving any farther, it's like a wall, and they can only go so far, and then they're stuck between literally a rock and a hard place. So the ocean's coming at them one direction, and they can only go so far because there's a barrier there, and so they get squeezed. And so this phenomena has been coined coastal squeeze. And that so you can see a couple different well, you can see how this works. So if we have a seawall here, right, or a bulkhead, so you see along a lot of coastal subdivisions, and a really good example of this is along Lafitte's Cove. So if you go down to the Lafitte's Cove subdivision, you'll see seawalls all around and within there, and they're concrete seawalls. Well, if you had a marsh in front of that seawall, or if you built a marsh, which they did actually along some of those canals, um, those marshes don't have anywhere to retreat as that water rises. So the consequence of that is if there's not enough sediment trapping occurring within those marshes, it's allowing that elevation to rise as a factor of that action, then there's really nowhere for them to go, and they will in fact drown out as a result. If you don't have that, then you have some opportunity here. And this says land reclaimed typically because of agriculture. In our area, it's primarily for development, human development. So what's going to happen to these salt marshes? Well, there's been a lot of work done on this, and a lot of different places are working on it. There are researchers within the Texas A&M system, within the UT system, universities around the country, a lot of private entities also studying this. And so this is just one particular model. If you look at Mustang Island south of us, down the coast a little ways. You can see predictions here based on different sea level rise amounts. So, if you look at the current marsh values, then you see where all of that coastal low marsh is, right? So this would be those Spartina alterniflora marshes. Given, thinking about the IPCC projections, this would be kind of a conservative estimate of relative sea level rise and then a higher estimate. So these blue areas are where that marsh is converting to water. And as I said, there's been a lot of work on this. And essentially how this works is this. If you look at a cross section of a barrier island like Galveston, what you see is sea level rise is occurring both on the Gulf side of the island and on the bay side of the island. So over time, if you look at a combination of sea level rise and erosion, you lose wetlands. And so areas that had been high marsh or upland areas become those future low marshes, right? The upland continues to move further. The core of the island and some of these center areas, they tend to remain intact. So you don't see a lot of changes here. But then these are also areas that tend to have the highest development rates. A lot of times, these wetlands, for instance, we're going to see a little later in the semester, these freshwater wetlands don't benefit from the same regulatory protections that some of these other wetland types do. And so it's a little easier to develop those. These areas then become hardened. Meanwhile, on the Gulf side, the beach dunes are also eroding and moving inland. So you get some narrowing of things like these protective ridges that we've looked at before. So on Galveston, there've been a number of studies. This is one. So Jim Jabot, who's and now he is with, I believe, Texas A&M Corpus Christi, but he was previously with UT Bureau of Economic Geology, and they did a study for the city of Galveston looking at sea level rise rates relative sea level rise rates, and they used LIDAR to develop a lot of their modeling. So a lot of the base maps that they did were actually LiDAR images. So you're looking at a colorized version of such an image here, and you can see the different habitat types that are modeled here. This is not dissimilar from what you'll see in a lot of the links that I'm sharing with you. If you ever use the U.S. Fish and Wildlife Service's wetland mapper, similar sort of thing. So it'll give you these different habitat types, and these are based on GIS projections working off of this LiDAR imagery along with other types of imagery. And so here you got this baseline. And then if you go forward 60 years, so, right, here's our original, here's 60 years later. And that is the effect of relative sea level rise. And you can see that the low marshes in particular have been really hard hit. Now, one of the things I want to point out is that when you get back into here, there's a lot of housing and infrastructure, right, that occurs along. So we've got roadways here. There are subdivisions that occur back in these areas. And so some of this is not going to change because it's hardened surface. So these areas are the areas that are most likely to get squeezed out. And when we look at these then biologic communities, what this modeling suggests to us compares well with what actual measures have shown over the last 50 years. So you see an increase in high marsh, the relative amount of high marsh, and you see a decrease in low marsh. So that's what the modeling that Jim Jabot, his study did. We've seen this in other studies as well, and it corresponds generally to what we're seeing in terms of overall wetland trends that includes both of these types among the others. That mid-marsh would be included in that as well over a period from the 1950s through the early 2000s, right? Okay. In fact, the Bureau of Economic Geology developed a hazard map that was never published because there was a lot of concern about how this might impact other aspects of socioeconomic impacts of the Galveston community. But they did, this was put out for public review, and that data showed the areas that were most potential to geohazard type threats. So when I say that, you can hear relative sea level rise, right? And so these red areas where it's imminent, where this is going to happen very quickly, okay, within a decade or two. And then as you move further out, then over time, it's going to take longer for those areas to be impacted. And then some of these lowest areas are these areas that are in really that high ridge in the middle of the island that, again, a lot of times tend to be more highly developed. Now, one of the things I want to point out is you have this area right here, right, that's developed. This is a canal subdivision, and you can see that it's a different color than what's around here. Part of that is because there's been some shoreline hardening that's happened there, and this has been raised to support housing, right? So there aren't really wetland communities here. These aren't biologic communities. These are, urban, suburban, residential neighborhoods. And so the hazard has been reduced somewhat because this has been raised and there's been some hardening. But when we're talking about coastal plant communities and the biologic and biogeochemical functions that they provide that support our economy, that there's this significant problem. Okay, so then one of the questions has to do with, well, can salt marshes accrete fast enough to keep up with this phenomena? And the reality is probably not. In many areas, you see a deficit where there's just not enough accretion to keep up with relative sea level rise. Now, this map shows the areas, the red areas show the highest levels of RSLR. And this is, again, true in the Gulf of Mexico because we don't have the amount of sediment feeding into the Gulf via the Mississippi River that we've historically had. And that has robbed us of a significant amount of sediment. And so there is a lot of work actually occurring with our federal agencies in particular, in cooperation with state agencies, looking at how can we manage sediment flow through these dams while also protecting the features that the dams are there to protect. And it's a real challenge because some of this infrastructure has been there for 70 years or more. And in some ways, there's been communities. One of the things that happens a lot of times when you put in a dam or a levee is that people build right up behind it. And now you've got this embedded community that's protected by this man-made structure that's causing another problem that we didn't really realize at the beginning. So it does create some particular issues. And so the Gulf of Mexico is one of those hotspots. There has also been an acceleration in sea level rise, and this is across the entire east coast of the United States. And I know I've talked to you about how there are a lot of similarities from kind of the mid coast, kind of south in New England, but kind of mid-Atlantic all the way down into the Gulf of Mexico. You see a lot of the same habitats, you see a lot of the same species, and it turns out you see a lot of the same factors occurring. These extend even further up into New England. And what we're seeing is sea level rise increasing, the trend increasing, especially once we got into the last decade, right? And so you can see these trend lines, and it's not the same everywhere. And part of that has to do with the different natures of the soils that are involved, different natures of groundwater, sediment budgets, erosional trends. All of these things are tied together. So it's not just one factor, it's a lot of different factors playing together. So they're not identical, but here again, the trends are surely consistent. Okay, so we've seen what's going to happen with coastal marshes. Is there a similar effect with mangroves? And in fact, there is. When you look at this data, we can see that these species, like the marsh plants, are highly adapted to their specific environment. They have a range of tolerance for different conditions, especially the level of the water that they live in. So when we look at distributions based on these increasing water levels, we see changes in those distributions over time. What about freshwater wetlands? Well, again, it's again the same trends. As the water rises, you get penetration of salt, for instance, up into these freshwater zones. You also have higher levels of flooding, which freshwater wetland plants, these marsh plants, are no less susceptible to being drowned out as saltwater wetland plants. They might be different species, but again, they're adapted in analogous ways. And so, with a 70 centimeter RSLR prediction, you would expect more than 20% of freshwater wetland loss right in Galveston Bay. And if you look at this map, here we go. You can see here that a lot of these losses are occurring over in the Chambers County area. This is a particularly low area as it is. So this is an area that tends to not be very far above sea level. If you've ever spent any time out here, a lot of this has water on it throughout much of the year. So it doesn't take a whole lot for water to get higher in those areas, for salt to penetrate, and for those communities, those freshwater wetland communities, to start to change. You see a lot of that here along and Brazoria County and some of Galveston County as well. Similar sort of environments in those areas. Dunes. So we talked a little bit about dune habitats. Well, here again, we got to look at coastal squeeze. So if you spend any time down on Galveston's beaches, you should, and certainly since we talked about this in class not too long ago, I hope you have noticed that there are multiple dunes, right? You have those primary and secondary dunes, you have those swales, and where you have houses right at those primary dunes, which a large part of West Beach has that phenomena. Not only does it destroy the habitat of the secondary dunes and a lot of those swales, but it puts those houses at very significant risk, because that primary dune is really the only protection those houses have. And what the dunes are going to try and do as they erode and they're impacted by sea level rises, they're going to try and go back. So it's again that coastal squeeze. Can they get past all that infrastructure that we've put in there in terms of those houses and the roads and all of that to be able to move and migrate back? The big question. When we talk about built shorelines or constructed shorelines, it's if there's plant communities associated with those, so think living shorelines. I know I've talked a little bit about that in some of my own coastal research. What we find in our living shorelines is that if they're designed appropriately, they're designed with a room for them to migrate as sea level rise occurs, then those marshes tend to persist. And we are actually seeing that, and we have data to that extent so far. So that's good. But again, design matters when you're looking at these. Truly hardened structures like what I'm showing you here, there's no migration, there's no biologic community typically associated with those to any magnitude. If there's riprap and things in front of it, you'll have some rock dwelling organisms. But But in these instances, what we see is that these tend to be more prone to undermining and failure over time, like any seawall, right? The water is like little shovels. Every little wave and current is just digging a little bit of sediment, and eventually you can find undermining, and those walls will start to fail. So that will certainly increase infrastructure costs and recovery costs if that's the case, and that's why one of the things you tend to see is, oh, sorry, I'm a little ahead of myself here. One of the things you tend to see now is efforts to try and build beaches out in front of where these sea walls are and keep those beaches built up, even with dune structures where they can do it in order to protect this infrastructure. We also see the impacts of tides. So this has been particularly highlighted in the southern Florida area and in the Keys. I have some friends that live in the Keys, and um, so you see a phenomena referred to as king tides, and king tides occur when you have spring tides associated with perigee. So if you're not familiar with perigee, or I'm sorry, perigee, not perigee, perigee. So perigee is when the moon, for instance, is at its closest orbit to the Earth, and during that time, its gravitational pull is the highest. So you've got a combination of a spring tide and then this perigee that creates these exceedingly high tides. And so you have areas that will flood when there's no storms, there's nothing else going on. It's just pulling those tides in. And that is, again, a secondary effect of relative sea level rise, where you've had erosion, you might have had some subsidence along with sea level rise. It makes those areas more prone to these types of tidal features. So, and yes, I do believe that is an octopus. So, all right. So, in summary, right, we've talked about sea level rise, and really we spent our time talking about relative sea level rise. So add an R in front of that, and then that forcing an inland migration of most of these coastal habitats, and this can be impacted by coastal squeeze. So development of infrastructure, houses, roads, that kind of stuff, bulkheads, topographic features. So natural features, some can, in some cases, create problems that won't allow those low habitats to actually move inland. That's not, I would say, quite as typical here along the Texas coast as it is on coasts in some other parts of the United States and other places globally, but it can happen. You have a particularly high area, it becomes really difficult for those plants. If you've got a steep slope, there's not a lot of space there for them to be able to maintain their functionality as a community when the bands get to be too narrow and there are too few numbered individuals within each biologic population. So, part of the problem we have also is regulatory, and how our laws and processes and how our economies are, how far in front of this or behind this are, and it's not equal. Again, like we were talking about with warming in the oceans, it's not homogenous. Some things do better than others. For example, the Clean Water Act right now probably isn't well attuned to coastal sea level rise, because a lot of wetlands that will be impacted by this phenomena are not really addressed within the regulatory structure, and thus they're more prone to development, which then leads to coastal squeeze. So there's estimates that we're going to lose probably in the neighborhood of 30% of our wetlands in a reasonably near future, right? Maybe even within my lifetime, right? Certainly within yours. All right, so quick clicker question. So RSLR stands for which of these? Well, if you chose B, relative sea level rise, you are correct. A coastal road acts as a barrier preventing a salt marsh from migrating to higher elevations in response to sea level rise. As a result, the marsh area decreases. This phenomenon is called what? Coastal squeeze, right? So here, coastal squeeze. All right, so let's look at the implications of this phenomena as it applies to coastal species distributions. So we talked a little bit about mangroves and how their trends are likely to follow that of coastal marshes and most other shoreline species, and that they're going to try and move upslope. So when we look at the Gulf of Mexico, and particularly along the Texas coast, we've really got two species that are prevalent. We've got our red mangrove and we've got our black mangroves. The Avicennia is the black mangrove, rhizophora, the red mangrove, right? And so what we expect based on what we see now, which is what you're seeing here. So our current distributions of mangroves are pretty spotty, right? And so you've got areas here that just aren't prone to that. However, if we look ahead towards the end of the century, so about 25 years out, the amount of cover, because those areas are going to become more flooded and therefore more um, uh, better suited for the types of mangroves that we have along the coast. And they're going to become saltier as well because as that water from the Gulf of Mexico starts to permeate up into the coastlines, into the rivers and creeks and bayous, that's going to allow those species to migrate up into those areas as well. And again, it's not going to be homogeneous. Some areas it's going to be lesser. But in areas, especially in areas where it's very warm on top of it, so though all of those factors are going to benefit increasing mangrove distribution as we move forward in time. And we're already seeing that to a certain extent. We're seeing more black mangrove, for instance, that Avicennia here on the northern part of the Texas coast. We're seeing increasing distributions already. So again, these projections are pretty well in line with what we're seeing now. So what are some other possible outcomes of increased temperature? How will habitats and species distributions happen in, sorry, let me try that again. Will changes in species distributions happen in other habitats? Will growth rates change? Is there likely to be changes in seasonal reproductive patterns? Could migratory species be impacted that currently use these coastal habitats? Yes, is the answer. Um, so we're likely to see changes as the habitats change. The biologic communities that access those habitats. I'm sorry, I'm a slide ahead here, but these distributions are going to change. Growth rates are going to change because of increases and changes in temperature, along with other abiotic factors. And then that's going to change reproduction because some reproduction, while some of it's light driven in plants, there's also temperature patterns that occur in a lot of species. We already see this with migratory species. So, yes, these things we expect are going to change as these habitats continue to change. All right, let's look at precipitation here for a minute. So, here again, we've seen this over certainly over the last 25 to 30 years. During my career, the height of my career, we certainly see this. In general, wet areas are getting wetter. So um, Houston, Galveston, Beaumont, this area is generally along the 30th parallel. And the 30th parallel is an area where you have convection currents that are falling. So these are areas that would typically not get a lot of precipitation. So if you follow the 30th parallel, that latitude line along the globe, those areas in general tend to be drier than areas further north and further south, right? So technically, we should be in kind of a dry area. Right along the coast, we're very much impacted by the humidity and moisture because of the Gulf of Mexico. So that's why if you go inland from the coast here on the upper Texas coast, even just 100 miles, the climate starts to change really rapidly and it starts to get a lot drier. For those of you who've driven across North Texas, any of those areas, it's considerably drier than it is over here on the coastal part. So The wetter areas will tend to get wetter while the drier areas will tend to get drier. And we see that in the data. Here along the Texas coast, we are continuing to get wetter. The precipitation rates are increasing somewhat. The drier areas, especially in North Texas, Central Texas, are getting drier. And as a consequence of that, we're seeing some changes in salinity. Again, largely because, and I'm speaking specifically with the Texas coast, but a lot of the Gulf Coast, a lot of the water that feeds into the Gulf of Mexico is not coming directly from the coastal margin. It's coming from inland areas via these larger rivers. Hurricanes. So a lot of discussion about hurricanes. We are, of course, in hurricane season still now as I'm pulling this lecture together. Um, there's been a lot of discussion about and a lot of studies done on whether warmer ocean temperatures are going to increase the intensity and frequency of hurricanes. Intensity, it is most likely to have an impact in intensity, and we're already seeing that. We're already seeing evidence of that, as especially here in the Gulf of Mexico, as these waters are getting warmer, but in the Atlantic as well. Storms are getting stronger faster. They are developing faster. And that's because that temperature of the water creates more moisture into the convection currents, gets it into the lower atmosphere, and that air is moving faster. Everything's happening at a faster rate, and consequently, those storms are developing much more quickly to much higher levels of magnitude. So instead of, over the course of 2 or 3 days going from a tropical wave to maybe tropical storm or a Category 1 hurricane to going from blob of clouds to a Category 3 storm in a matter of 3 days, right? And we've seen that consistently over now several years, and I would be surprised if that changed, based on the data we have. In terms of frequency, I think we don't have enough data now at this point to be able to suggest that's going to be the case. So I would suggest stay tuned. There are a lot of contributing factors to how storms form. So once they form, once they start to form, there's the factors are there, and that warm water causes them to develop more quickly. But the initial formation is really very impacted by things like atmospheric circulation patterns, dust storms. So again, we get dust feeds off of the African coast that come all the way over here and deposit in Texas, and that dust can slow those convection currents down, and kind of tamp those storms down and prevent them from forming in the first place. Ocean currents also, because of the way they move heat around, the temperature of the oceans in any given spot can change, not only from year to year, but also from month to month in ways that are not going to be consistent from one time frame to the next to the next. So it's fairly complicated. So I think you're going to be looking at some years more data collection before we're going to be able to really speak to frequency very well. All right, so what's the link to coastal wetlands? Well, the link here is that these wetlands provide an ecosystem service by buffering storm surge impacts, right? So fewer wetlands mean less protection. The general rule of thumb is that for every 2.5 to 3 miles of marsh, you're attenuating storm surge by about 1 foot, okay? Now think about 2.5 to 3 miles is not very many miles inland, okay? It's fully 50 miles from downtown Galveston to downtown Houston, right? I mean, you're talking about a long ways. So a little bit of marsh can have a really significant impact on the amount of and the intensity of storm surge. So this loss of wetlands in our area, for instance, along the Texas coast, certainly has increased the probability of surge impacts. And that's why one of the reasons why there's been so much focus on restoring wetlands and taking the opportunity to construct wetlands where they are likely to do well, right? So things like the Living Shorelines programs that I've worked with the Galveston Bay Foundation have a lot of value in terms of this improving this ecosystem service, right, and restoring it more to its historic levels. Um, this data, by the way, is based on inland extended storm surge from a handful of storms between 1909 and 1957. And there is some variability depending on where you are, because again, there's a little more to that than just how much marsh is there. So this is, again, why we call it a rule of thumb. Okay. All right. So generally, this has to do with energy dispersal, right? And how marshes store water. So just with hurricanes, marshes do a lot of the same things they do with everyday wave energy, right? The plants break up the energy of those waves. And when you break up that energy, it slows that water down in every given spot, right? And that allows for that energy to slow down, so that water's not going to penetrate as far. It also has the effect of pulling sediments out and all those other things we've talked about previously. But that energy dispersal function is really important. Um, Also, there's water storage. So wetlands have long been um, known to be really important flood mitigators in inland areas. You know, one of the problems downtown Houston has with flooding after big rain event type storms, so think Hurricane Harvey, is that a lot of our inland bayous have been developed right up to the flood line, essentially. And many of them have concrete liners in them, so there's no natural plant community to break up this wave energy or store the water, right? So, and it's that water storage that's particularly important in those areas. So you want, when the water flows into those areas, you want to hold on to that water and release it slowly so it's less likely to flood downstream areas. Well, if you look at how the spreading of human communities out into the landscape surrounding Houston, areas in the, think Katy, Sugar Land, the Woodlands, all these different areas where you have so many houses and so many roads, so much development, hardened surface, and building right up to the water lines. So you can charge extra for those houses, right? There's nowhere for that water to sit, right? So it's all going to flow into the bayous and then flow out, and then it lands all in downtown Houston before it finally makes its way out to Galveston Bay. Well, that's true also in these coastal areas. So that water will go up into those coastal areas. The plants break up the wave energy. They break up that storm surge energy. That storm surge kind of dies out in those areas, and those wetlands hold on to that and they release it out more slowly, which then protects those most coastal areas from erosion as that water is rushing back out. This is a pretty neat video. So when I post this, I would encourage you to take a look at this. And it kind of shows how that works. This is a mesocosm that shows how that actually works. All right. So, again, like everything, nothing is quite as simple as we'd like to paint it. Storm surge is complicated, and there's a lot of things that impact this. So the geometry of the shoreline, the vegetation type that's present, the slope of the ocean floor offshore can have an impact. That's why storms, as they come on shore, oftentimes weaken where there is a long, shallow continental shelf, but where it's just deep, they can really slam into those shorelines with a lot of intensity. The speed, direction, size of the storm, all of that stuff has all of these have an impact. And wind speed, which is usually greatest in the northeast quadrant, okay, not a quadrat, which is an area of measure, but the quadrant is often strongest as well. So where it's coming into shore, and if that northeast quadrant is going to be the first area to hit the shoreline, that can impact what that storm surge is going to be as well. So I don't know if any of you would remember Hurricane Rita. I remember that because that was a storm that we evacuated from. So in 2005, we went south because hurricanes in the Gulf of Mexico tend to take their turn to the north and then eventually move back east. That has to do with overlying air currents. So we fled south down to Corpus Christi, which is actually where Rita was supposed to hit in the first place. And so that all worked out for us pretty good. But you might have seen pictures of the hundreds of thousands of people on the roadways stuck because there was nowhere for them to go because the roads were all filled up. Well, fortunately, the storm took that northerly turn a little earlier than it was predicted. That was good, which meant that the worst part of the storm, in terms of wind speed, missed us here in Houston, but the western Louisiana shoreline was very exposed to that. Fortunately, it was moving fast enough that it was only for a short period of time. But that's also an area that has extensive coastal wetlands, and combined with the short time frame, how quickly the storm moved inland, the attenuation factor of those plants on the storm surge was pretty close to that 2.7 estimate. So it was pretty significant, right? And that in turn saves a lot of people's lives. It saves property and mitigates a lot of the secondary problems that come along with the impact of these storms. So you can, at the time I'm recording this, Hurricane Helene hit just east of there, and you can see the huge damage associated with that storm where that attenuation wasn't as significant. Of course, that was a really actually a stronger storm as well. Okay, so in eastern Louisiana, where it was exposed to the northeast quadrant for nearly a full day, all right, even though the wind speed was lower, the duration of that wind was much longer. And so water piled up along levees, which are more prominent there than they are in western Louisiana. Those marshes became inundated, and the levees caused the surge to actually increase over those areas. So the marshes actually became completely flooded as a result of that. So we can actually do things, changing the landscape, that impact whether or not these ecosystem functions associated with these marshes are going to be as effective or not. Now, you probably do remember Ike, which was only just a couple of years later. Many of you may have been really, really young, but again, this is one I remember very clearly. It didn't have the wind speed that Rita did, but it was larger and it was moving more slowly. And so the surge moved much further inland because of how slowly the storm was moving. It gave a much more opportunity for the storm to maintain that surge. You know, I think I've mentioned this before, but in Baytown, we had 19 feet of storm surge at the wave caps, and it moved a long way inland. Part of that was because many of the marshes that historically had been there have been converted into upland environments and hardened surfaces. But there was also a lot of marsh loss associated with Ike along the Gulf Coast. Some of that had to do with inundation from sediments. Some of it had to do with losses because of the intensity of the storm. So, different storms, different landscapes. Sometimes you get different effects there. But by and large, again, the more marsh you have, the better it's going to be able to mitigate storm surge. So the bottom line here is that the role of coastal plant communities in terms of attenuating storm surge is variable, but it's usually beneficial, right? They never can hurt anything, and sometimes they can really help a lot. So if you look at these two buildings here in the east end of Galveston, they had a substantial low, mid, and high marsh here associated with these dune structures that are along East Beach. And those dunes did their job, right? They really helped when Ike came in terms of preventing losses further inland. Now, not to say there's a lot of loss there when you look at the comparison between these two pictures, but actually for these buildings, that worked out really well because they were protected by the ecosystem services that these wetlands actually provided. And you saw this up and down the east end. This is another picture from that same site at ground level. You see things where by comparison, if you go down by the seawall where there aren't any plant communities along the seawall, these things, where there was sand, where there was beachfront, that sand gets moved very rapidly because there's no dunes to buffer them there, right? And in part, that's why there's the riprap rubble that you see along the toe of the seawall. It is to mimic some of the features that the plant communities would provide by breaking up that wave energy. That riprap is hopefully going to break up some of that wave energy, which will prevent undermining underneath the seawall itself, right? Okay. So we talked about, I actually mentioned urban flooding earlier, and I will say in all of my work dealing with inland flood risk, all the way up and down the East Coast. So I've done work along the Rahway River in New Jersey, did work along the eastern part of the Gulf of Mexico. Here in Houston, I was involved with Buffalo Bayou demonstration project with Harris County. Done work again up in the Pacific Northwest. Uh, so in any event, all of these areas have common elements in terms of how flood risk is. The individual communities, biologic communities, might differ by the types of species that are there, but the functions are analogous. Um, so flooding events in all of these areas are very strongly linked to how many wetland alterations there are, how much these wetland communities have been modified anthropogenically, right? Um, and what we're learning is that urban environments can benefit substantially from restoration of wetlands that historically were present along these inland waterways. So that includes shoreline marshes, that includes riparian habitats, so riparian forest, for instance, that we have looked at earlier, swamps that are associated a lot of times with even more inland areas. These wetlands can mitigate this flood risk by, number one, attenuating the flow of water inland in the first place, but also then holding onto it and slowing down its egress back out of those environments and back down slope as that happens. So that's really, that's a substantial issue. Some areas are more impacted than others when we talk about conversions. So there has been a lot of emphasis on going back and modifying previous shorelines. So I'll use Houston as an example. There's a lot of effort now to restrict build outs right up to the shoreline of the bayous. So there have been buyouts where historically people had been allowed to build houses in the floodplain right up to the floodway. Now, those houses in many instances are being bought out by Harris County in order to restore the floodplain so that it retains or rebuilds these ecosystem services associated with the wetland and other plant communities that were historically associated with those the floodplains, right? In some areas, you see development of shoreline wetland environments as an amenity. So there's a recognition that people do value green spaces, and so you can incorporate these green spaces along with these ecosystem functions to restore some of these features. So where you had historically seen, and Buffalo Bayou is a good example of this, where you've seen, historically a concrete line channel that was essentially a glorified drainage ditch. Brays Bayou is another one I used to live right off of. There's been efforts to go back in and restore portions of those in order to restore the original wetland features and even reshaping them in many areas to mimic more of a natural shoreline that would slow down that water flow as it's moving in and out, giving an opportunity not only to mitigate flood risk, but also has water quality improvement benefits as well. All right, so the other thing I wanted to talk a little bit about was ocean acidification. And so this is kind of an interesting thing. And this cartoon, by the way, is funny. I can't take credit for it. I have to give my colleague Anna credit for this. This is a really good one. So yeah, you know that all of these acronyms now have double meaning. So CO2 that we've been so concerned about in terms of how it impacts climate also impacts the oceans, right? So just like heat energy is absorbed into the oceans are also a sink for carbon dioxide. Gaseous carbon dioxide dissolves into the water, right? Dissolves into these ocean environments. And so that is directly affected by the concentration of the carbon dioxide in the atmosphere. The higher it is in the atmosphere, the faster the dissolution rate into the ocean. Okay. And so what happens is that carbon dioxide combines with the water, and you get a chemical reaction, right? Remember the difference from your chemistry class between chemical and physical reaction. So you get a new product here in the form of carbonate, right? And so that carbonate, H2CO3, then further reacts and it releases the hydrogen ion and leaves behind bicarbonate, right? And so that hydrogen ion, remember the pH scale, okay? So as the pH increases, you have a more alkaline environment. And so that's associated with hydroxide ions as you have an increase in hydrogen ions and the pH reduces, then you have a more acidic environment. So this release of that hydrogen ion lowers the pH, which increases the acidity, which then can have a significant impact on organisms whose um, body structures, so coral, for instance, that have a large amount of calcium as part of their skeletons, then are more susceptible to those shells being impacted by those acidic environments and dissolving. And they can actually prevent the formation of new skeletons if the animal is trying to heal. So this can obviously impact coral, and we see quite a bit of that. Those of you who spend any time out at the flower garden banks, which are not nearly as impacted as some other coral reefs around the world. But also other types of organisms, snails being another one. So this ocean acidification is something that compared to some of the things that tend to impact us that we spend more time focusing on, um, corals are kind of the rainforests of the ocean, right? And so, in terms of the habitat value that they offer, including to many species of pelagic fish that spend part of their time actually up in our wetlands, are important food sources. They perform important ecosystem services and are important parts of our economy in multiple ways. Are impacted by this phenomena, and really we tend not to see that as clearly as we see flooding, coastal flooding. So I don't think this has gotten as much attention in the general public as it does perhaps with us that are in the sciences. All right, so I want to wrap this up by talking about what can we do about this. And I would say one of the most important thing is you have the advantage of getting an education in this subject area that gives you insights that many people just don't have that advantage and don't understand. So that calls to you to show some leadership in these areas, either at the personal or the professional level or both, right? Part of that is developing an understanding of where carbon emissions are coming from, what those sources are. One of the unfortunate things that has happened in the sciences, I think, during the course of my career is a continued siloing of different disciplines. And I think that has changed a little bit in the most recent years. In the last decade or so, we're starting to see again more emphasis on interdisciplinary work. And so just because you're a fisheries biologist doesn't mean you can ignore what's happening in terms of carbon budgets in the atmosphere, because there is a linkage between those two things. So working interdisciplinary in an interdisciplinary manner, and keeping in communication with colleagues that are studying or working in different disciplines is valuable for you to be able to not only have an impact in your own field, but also to have an impact in your community as a whole. That may start with your family, by the way. So we have learned how we can prepare, and I would avail you to take a look at what efforts are occurring. The Texas General Land Office, working with the U.S. Army Corps of Engineers and a number of other federal and private entities, federal and state agencies and private entities, are working on a coastal mitigation plan that includes a lot of plant community infrastructure and restoration. You can find a lot of that information here. I had the benefit of actually working on part of that up in the Beaumont, Sabine Lake area and down in the Freeport area some years back now. And you can actually read about that. And I think I have links in my CV, which I think I put on Canvas. If I did, and I certainly can. You can find those things. But anyway, those are linked here as well. There are a lot of ongoing efforts to mitigate losses to these ecosystems. And again, looking at this type of work can give you some insight into the types of steps. Not only are these major metro areas, for instance, the city of Houston, I'll talk about here in a second, but other areas along the Gulf Coast, to mitigate their own greenhouse gases, recognizing that these major metro areas oftentimes have an outsized impact in a lot of ways. But also, they also tend to be the areas that really need to focus the most on adaptation and mitigation, because they tend to be subject to the most types of damage. So Tropical Storm Alicia back in the early 2000s, Hurricane Harvey, had huge impacts in the city of Houston, and a lot of that was related to flooding, right? And so we've seen a lot of emphasis on mitigating for those and figuring out, okay, we know we're going to have more issues related to sea level rise, increasing intensity in storms. So what can we do to prepare for these kind of things? And so your career might take you in that direction, but certainly if you're going to continue to live in the Gulf Coast area and work in this area, on a personal level, and even just for your family and friends, you have an education that will allow you to help everybody help themselves, right? Um, Houston, unfortunately, Houston has one of the highest per capita greenhouse gas emissions in the country. A lot of this is linked to transportation. Everybody has to drive everywhere, and as Houston has so much sprawl, it takes me an hour if I want to go from Baytown to Katy. It's going to take me an hour at best with little traffic. If there's a lot of traffic, I might spend up to an hour and a half or more trying to get through all of that. Same getting from Galveston to Clear Lake. I sat for 30 minutes on the road the other day just because of a stop due to road construction, right? There's a lot of people, a lot of cars, and even though Houston is very sprawled, we're talking about nearly 5 million people in an area that is really only a small portion of the state as a whole. Now, the good thing is that Houston, along with the entire state of Texas, is continuing to benefit from the growth in green energy and transportation options. So Houston, because of its density, is putting a lot of effort into mass transport. There's a lot of effort to provide alternate transportation that utilizes green energy. So you'll see buses that are electric. You'll see a lot of service vehicles, even in the private sector now, are becoming electric vehicles that are charging on these industrial size charge facilities. And because of the short nature of the distances they have to travel, they're able to do that, which really cuts down on air pollution, including those air pollutants that have high carbon levels that eventually become greenhouse gases. Houston is also the #1 municipal purchaser of green power in the entire United States. And in 2017, for instance, the city of Houston used nearly 1 billion kilowatt hours of green power from solar and wind. And believe it or not, Texas has one of the highest production levels of wind energy anywhere in the country, of any state in the country. We make more wind, and not just in Austin. Ha 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 ha. Because where the capital is, come on. So, but rather, a lot of West Texas, if you've ever driven across Central and West Texas, there are a lot of windmills, and that produces a lot of energy. And that energy does find its way over here to the Houston area. So it's significant, and in the city of Houston, it's continuing to grow, and that does overlap with Galveston County as well. All right, so you can also take individual actions. I know I've mentioned the tragedy of the commons. What I'm going to do isn't really matter because I'm just one person, and if I don't do it, somebody else is going to do it anyway, so it's not going to matter because everybody's going to be doing it. Well, if everybody thinks that way, then it's certainly going to be a problem, right? So we need to think the other way. The little bit I do does matter. So we need to consider our own individual actions, and that doesn't mean you can solve the whole problem by yourself. Rather, it means do the easy things, right? Do the things that are easy that are going to help the problem, right? So, when you're going out to run an errand in your car, instead of running an errand, coming back home, and then a while later going out and running another errand, and then running another errand, bundle those things together, right? Try and do those things in a way, and try and make all your errands kind of as close together as possible. That is a really big impact. The number of miles that you cut down doing that can be really significant. Paying attention to your energy usage. And one of the things I would highly encourage you to do, and I will be happy to talk to you about this, is figure out where the heck the energy you're buying to power your home or your apartment actually comes from. Did you know you have tremendous amounts of choices? And those choices allow you to choose green energy options that are totally renewable. And in most areas, they're little if I'm sorry, they're not really much more expensive than non-renewable options. In fact, in some areas, including where I live, it's actually cheaper for me to buy renewable energy than it is to buy non-renewable energy. So you can go to a website. It's called power2choose.org. .org. And that .org is really important because there are a number of mimic websites that are private sector websites that are trying to steer you towards their particular products. So power2choose.org, and look and see if you have options, and look at the pricing of those options. Like I say, at my house, we're 100% renewable, have been for many years, and it's partly because of my beliefs, but partly because it's cheaper, and I make a faculty salary, right? So there you go. So these kind of things can have a difference. Where your food comes from, buy local if you can do that. So I really like this graphic for that reason. Um, I think there's also value in being optimistic. In the sciences, especially on this subject, we can be very doom and gloom. And the consequence of that is really problematic because if you feel like whatever you're doing isn't going to work, then you're probably not going to keep doing it. And it definitely won't. Right. So there are some really good researchers doing a lot of really good work out there. Catherine Hayhoe is one in particular that works with Texas Tech that I really like her attitude and projection. But there's a lot of really good researchers out there that are really quite positive about it. And I am too, because you know what? A lot of the solutions that we need in order to solve these problems are already on the shelf. It's not like we need to develop new technology in order to tackle a lot of the worst parts of our carbon manufacturing into the environment. Rather, those things are already on the shelf. It's more a matter of deciding to use them and employ them, right? And that's the part we're stuck on. That's the part we've got to change. But being optimistic that if we do this, it's going to make that change certainly helps project that forward. And we're seeing a lot more of that. And so I would encourage you to be optimistic because I certainly am. And I do see a bright future, but it doesn't mean there's not hazards. And if we don't do anything, then it's not going to be nearly as pretty as what I would suggest it could be. So, with that, again, you should be able to, after this discussion, be able to address all of these different issues. And one thing I want to remind you, for those of you in class, is that I did extend your weekly quiz. Next week, we have the first part of the week off on campus, and so I didn't want you to have to be doing this stuff during that period of time. So you can focus on other things. So I extended this out to the 15th. Okay. Thank you again for your attention. I know this was a little bit of a long one. There's a lot to cover there, but I hope it was enjoyable. I hope it was illuminating. And if you have any questions, please reach out to me. And thank you as always for listening. I'll see you next time.